All right, so this is kind of part two to what we were looking at. So before we had the astronaut and the tank moving, and then he throws it, and then we have them move off in equal directions. So we start off with some momentum, and then we have an explosion. So we're looking at here is a wheel, which we can treat as a hoop of mass 9 kilograms and radius 0.5 meters, is spinning clockwise at a rate of 20 radians per second. A person holding onto this hoop and steps onto a disc of mass 5 kilograms and radius 0.25 meters as initially at rest. The person flips the disc so that it is still spinning at 20 radians per second, but is now counterclockwise. What is the angular velocity of this disc? So that's a lot. Before we draw any pictures or anything, I just want to solve for the moments of inertia. So for the hoop, the moment of inertia, we say I equals mass times radius squared. 9 times 0.5 squared. That is 9 times 0.5 times 0.5. So we get 2.25 for the hoop. And then we have the disk. So the disk is 1/2 mr squared. So it has a mass of 5, radius 0.25. 0.5 times 5 times 0.25 times 0.25 is 0.15625. Alright, so if we're looking at what this situation is, it sounds complicated, but it's really just what you guys did in class. We didn't get to formally do it, but people did it enough, where we're saying, hey, we have this turntable, this plate that's not moving. We have some momentum in this first case because of this spinning hoop. And then a person stands on it, is holding the spinning hoop, and then flips it upside down. And in this act of flipping it, not moving, it switches the turning direction, and then everything begins to spin. So let's try it out. Let's do this question. Hopefully you're drawing some parallels already to that other question. Let's see, so a person holds on the hoop. So let's set it up just like we did. So L initial, L final, we have the hoop, and we have the disk. All right, so let's figure it out. So we know that initially the hoop is spinning clockwise at a rate of 20 radians per second. So we are saying, okay, its equation for angular momentum is L equals I times omega. The hoop has an I of 2.25, and it is spinning clockwise 20 radians per second. So clockwise we're defining as negative. So, and then the disk is not moving. So our total initial angular momentum is 2.25 times negative 20, negative 45, and that has to equal our final. So then the person steps on it and flips the hoop upside down. So that means it still has the same moment of inertia and the same angular velocity, but now our angular velocity is positive. And that means we're going to have some sort of I omega here. So we know already 2.25 plus 20 is equal to 45 plus 0.15625 omega. All right, so we can do negative 45 minus 45, negative 90 equals 0.15625 times omega. And if we solve for that omega, we get negative 576 radians per second. So this should look pretty similar to this astronaut one. It's just a little bit kind of reversed. So in this case, we had two objects moving, and then we have like an explosion. Here we have one object moving, and then we have this change in momentum of one of those objects, which results in a change in momentum of the other object. So I'll kind of let you draw those parallels as this video comes to an end.